In this video, I will show you how to implement a current controller for a three-phase inverter in the DQ reference frame. So this is how it looks like in Simulink. And if you look at the block diagram, it looks like this. This is the current loop. And now in order to understand it, we first have to look at the inverter itself. So this is just a screenshot of the Simulink inverter. Now we know that this voltage here is VM, and this voltage is the one we want to control. And this voltage is VL, which is the voltage over inductor, and we also want to control this using VM. So we just decide VL such that we get the current that we want. And then we have the voltage from the grid, which is VG. So since we want to control VM, we need to find an equation for VM. So by using the voltage loop, we know that VM must be equal to VL and then plus VG. So we know that VG is fixed, so we want to find VL. VL is quite simple to find in the ABC coordinates, but in the DQ frame, it's a bit more complex. So we know that VL, this is equal to the derivative of the current multiplied with the inductance. So in Laplace domain, we have S multiplied by L, which is inductance, and multiplied by the current, the DQ current. So this is also DQ coordinates. Now to get an intuition, I will just draw a phasor diagram where this is the D-axis and this is the Q-axis. And here we have a current IDQ. And if you take the derivative of this vector, you can see that it changes either that way or that way. But you also need to remember that the whole coordinate system itself is rotating with a speed of omega. So this means that the derivative, which is S, becomes equal to the normal derivative plus j omega. So the derivative is basically the derivative of the reference frame, which is this, and then the derivative of the current inside the reference frame. So you also need to remember or know that ID is basically the real value, while IQ is the imaginary value. So you can decompose IDQ into the real value plus the imaginary value. So this is expressed as a complex number. And you can also do the same for the voltage. Now, if you solve this equation here, you will get these two equations for the voltage in the D coordinate and the Q coordinate. So I will not show you how you do it, but here is a derivation of the voltages. Now, so again, remember that we have VM, which is what we want to control, and this is equal to the voltage over the inductor plus VG. Now, if we just look at the D coordinate first, we have VM and D. This is equal to, now we insert for this. So we have L times the derivative of the current over the change of time. And then we also add the grid voltage. Now, we also need to subtract this. I forgot that one. So minus omega L and then IQ. Now, we know this because we can measure the current. And we also know this because we can measure the voltage. But do we know this? And I would say yes, because we know the desired change of current and we know when we want it to happen. So let's say that the desired change of current, this must be the reference current minus the actual current. So it's how much we want to change the current such that we get to the reference current. And we want this to happen within the next switching period. So that means the change of time is 1 over the switching frequency. Now, if we insert this, we get that VMD equals L times the switching frequency, and then times the desired change of current. And then we also need to subtract the other things, like this one, and add the grid voltage. So this equation here is basically what we add into the block diagram. So you can see that here we have, well, first I need to say one thing. So you know that this equation is obviously not correct because this equation is ideal and the real world is not ideal. And you need to remember that the most important thing is to drive this to 0, which means that the real current is equal to the reference current. So instead of having a gain, it would be more robust to have a PI controller instead. Because the PI controller can change with time, and you can also set the gain that you want. For example, if you want a slow controller, you can have a low gain. If you want a fast controller, you can increase the gain. So if you look at the block diagram again, here we have the reference current, and then minus the actual current. So here we have the change of current, and that goes into a PI controller. And then this goes to the desired voltage that we want. And then we also have the grid voltage, and then we have a feed forward of IQ, which goes like this. And you can also do the same for the Q coordinate in order to get VMQ. But that procedure is basically the same. So now, if we go to the Simulink model that we have here, you can see that it's basically the same block diagram. So you have the reference, and you have the actual current, which goes into the PI controller, and then we have the grid voltage, and then we have the feed forward of the current. So this is just written in a fancy way because it has both D and Q at the same time. So that is why we, for example, have a matrix here, but it works exactly the same way. So the reason why we have a filter here, a low-pass filter, is because the actual current has a lot of ripple. So you can see that the yellow one is ID, and the orange one is the reference value for ID. So after a filter, you can see that we get no ripple, basically. So if we look at the results, you can see that the feed forward of the current is pretty low. So it shows that it's quite insignificant. And this is the feed forward of the voltage, grid voltage. So it's basically the grid voltage. And then this is the output of the current of the PI controller. So you can see that the Q coordinate is on average 0, while the D coordinate is not on average 0. So it should be on average 0 if the feed forward is very good. But you can see that we're missing something in the controller here, in the feed forward. And the reason why the D coordinate is not 0 is because we've not included everything here. So you can see that there is a resistance inside the MOSFETs, so it's 100 milliohms, and we did not include that. But the controller is still pretty good, as you can see. It controls the current towards the reference. Now, if you want to try out this controller, this Simulink model yourself, you can find it in the description below.